Okay, so again, huwag ka muna lumayo, Kajonel. Meron pa. Ito yung pangalawang tanong na pinadala mo. There's a second question by Sir Junel. Okay. This is his question. Let us read his question. A 250 volt, 6,600 volts, 50 hertz single phase transformer has a core section of 600 square centimeter. The flux density in it is 0.707 Tesla. Determine the number of turns in the primary windings. So what is the number of turns in the primary winding? Because you have a transformer. So that's step up, step down. That is a step up transformer. No? So let us consider you have your transformer here. Okay. That is your transformer. So we have here your coil, primary coil. Then you will have here your secondary coil. Now basically it has more turn. This is the primary and this is the secondary, because our given here is, how much is that? 250. That is the primary. 250 is to how much? 6,600. 6,600 volts. Meaning, the 250 here is the primary side of the transformer. And the 6,600 is the secondary side of the transformer. So we have the frequency 50 hertz. We have single phase. You're given the cross-sectional area of this core. This is the primary, secondary winding. Then we have the core here. Okay, and the flux density. The flux density is the magnetic field flowing here. Let's say we have a mutual flux here. Okay. You know the basic operation of a transformer. So I'll explain to you first the basic operation of a transformer. So we have here a primary source. Then we have a load here. We have a load. Okay. As we impress a voltage here, let's say we have a voltage of 250 volts here. So let's say this is our E sub 1. E sub 1. The secondary voltage is E sub 2. Okay? As we impress a voltage here, there will be current flowing here on the primary side of the transformer. So let's say this is our I sub 1. As the current I sub 1 flows in the winding of the transformer, it sets up a magnetic field in the coil. Always remember Ampere's right-hand rule. This is the current, this is the direction of the magnetic field. As the current flows in this coil, it sets up a magnetic field here. There is a magnetic field here, somewhere here. There are magnetic field flowing here. Okay? There are magnetic field here. As the current flows in our primary winding, it sets up a magnetic field. Then this magnetic field creates a magnetic flux that will flow in the air and that will flow in the core. So this is the transformer core. And this core will flow from the primary, this flux, this is the magnetic field. There will be a magnetic flux here. Due to the current I sub 1, there will be magnetic flux that will flow in the air and in the core. The core, the magnetic flux flowing from the primary going to the secondary winding, that is actually encircling in the core. No? Paikot-ikot yan dyan. No? So, that is the mutual flux. That is the flux that links the primary and the secondary winding here. Okay? As it flows from primary going to the secondary, this induces a current here. Okay? That induces a current in the secondary coil. This magnetic flux. This magnetic flux. There will be an interruption here. there will be a cutting of flux or induction here on the secondary side. That produces our E sub 2. Then our E sub 2 here, no, is an induced voltage on the secondary side. So you will have here your current I sub 2. So therefore, your I sub 2 here will flow through the load. Okay? So, we are given here, we have a primary number of turns, N sub 1, then we have here our N sub 2. Okay. So, we have what we call the transformation ratio. Ratio of transformation ratio, just the same. Transformation ratio of the transformer, okay, indicated by letter A. And our transformation ratio A is equal to this formula. So I just call this as any, E-N-I, any, E-N-I, any, E-N-I, any, 1, 1, 2, 2, 2, 1. Okay? That is any. Any. 1, 1, 2, 2, 2, 1. So that is any. Now, take a look here. Take a look here. If this is 1, this is also 1, then 2, 2, meaning they are directly proportional. What do we mean by directly proportional? As the number of turns increases, okay, as the number of turns increases, meaning you have more turns, meaning you will have a bigger voltage. Mas maraming ikot ng wire, mas mataas ang voltahe doon. If you decrease the number of turn, the voltage also decreases. No? Konting ikot, konti rin ang voltahe. No? Then take a look here. Take a look here. What about the relation of the voltage to the current here? What is their relationship? See? Their relationship is different. This is 1, this is 2. This is 2, this is 1. So meaning they are inversely proportional. Meaning, if you will have a large current on the side of the transformer, meaning that side has a low voltage. Low voltage. If you have a low current side, meaning that is a higher voltage side. What do I mean? Let us have a practical example. Let us consider you have a three-phase system, even if it is a single phase, just the same principle. You will have a three distribution transformer here. You have three distribution transformer that is connected to the distribution line here. Okay. That is connected line at phase A, phase B, and phase C. Then this supplies a certain restaurant. Question, which has a larger size of wire? Is it the primary or the secondary side? Saan mas malaking size ng wire? Primaryo, sekundaryo? Saan mas malaki? Mas malaki sa secondary side. Tama. No? Now, this secondary side is actually low voltage side, but it is high current. Why? Because this has a bigger size of wire. When you are sizing a conductor, if you size a conductor, it depends on the ampere. If you are sizing an insulator, it depends on the volts, on the voltage. That is why an insulators, they are expressed in volts, not amps. Okay? Oh, by the way, no, to all our viewers, no, in our Zoom class in particular, no, you may send in your question. I will answer live question later. If we still have time, you may type your question in the Zoom chat, no, in the chat board. Then I will answer your questions later. Okay? Or maybe you will have your follow-up question regarding to those topics I've discussed. You can have a follow-up question. Okay? Then later, I will answer that. Maybe around the 6:45 p.m., I will answer those questions. Okay? So let us continue here. This has a larger size of wire. A larger size of wire will have a higher current, will have higher current side, but it is low voltage side. So meaning, the primary of your transformer is high voltage side, but it is this high voltage, but it is low current. One sample voltage being used by the utility company is, a sample is, let's say, 34.5. Oh, sir, that's very low. No, it is kV, kilovolts. Okay? That is in kilovolts, not in volts. Meaning it is 34,500 volts. Okay? That is the line-to-line voltage on the primary side. Then on the secondary side, that is approximately 230 volts, which is the nominal voltage of the utility. Okay? So, in transformer, if you have the low voltage side, automatically it is a high current side. It is inverse. They have an inverse relation. If you have a high voltage side, meaning that is the low current side of a transformer, I am referring to the transformer, not the Ohm's law. Okay? Sir, I think it's a conflict. When we were in third year college, you said that as the voltage increases, you see, take a look here. You said that as the voltage increases, the current also increases. As the voltage decreases, the current also decreases. You said this when we were in third year college. But now you are saying we are now already in fourth year. You are saying the current increases, the voltage decreases. How is this? How is this? Because in third year college, no, when you were in third year, you are just studying Ohm's law, the direct current circuits. In direct current circuits, of course, our formula is I, that's equal to V divided by R. Of course, the relationship here, as the voltage increases, the current also increases. There is no transformer involved. There is a direct connection. Take a look here. There is a direct connection between the source. Let's say it has a variable DC source. So you will have here a load. This is how we experiment this in the university. So you have the load here. You have your ammeter here. And you have your voltmeter here. See? As we increase the voltage from the source, let's say this is the voltage, we increase the voltage here. Of course, the current will increase also. Okay? That will also increase. There is a direct connection of the source to the load. But if you are going to use a transformer, that will be in between your source and the load. It's a different thing. You have to consider the transformation function of the transformer, because this transforms without changing the power. It doesn't change. If you have a power here, let's say of 300 kVA, this is also 300 kVA on the secondary side. Okay? That is a transformer. It doesn't change the power. It doesn't change the waveform. Okay? Doesn't change. Okay? So, speaking of a transformer is a different thing. If you increase the current, meaning there is a low voltage. If you have a low current, there is a high voltage here. Huh? It's a different thing. That is the difference between the Ohm's law and the transformer. Okay? In the transformer, they have inverse relation. In the Ohm's law, they have direct relation between the voltage and current. As we increase the voltage, the current also increase. See? In transformer is different. If you have a high voltage, you have low current there. Okay? So we have to be very specific. Now, so anyway, that is just some transformer principle. Now, the question is the number of turns on the primary side. Okay? So we have to introduce a formula. What is the formula in getting first? Let's get first the induced EMF. I'll give you this formula. This is found in so many textbooks. Okay, in electrical engineering. So that is 4.44 frequency, flux, and then N. Okay. Remember, if I'm going to make this as 1, this should be 1. Primary, primary. This is the number of turns, the N. If I will make this as 2, make this also as 2, meaning secondary voltage. Okay? So, let us calculate this. Let us calculate this. This is a basic formula now. We have a basic formula here. Okay? So, we have here a magnetic flux. We studied last week or last Sunday about the magnetism, magnetic flux, magnetic circuits. Okay. The magnetic flux density is equal to the magnetic flux over the area. Remember, in our problem, we are given the magnetic flux and the area. If we are to get our magnetic flux that is equal to the area, cross multiply here, that is multiplied by the flux density. That is what we call the flux density. This is the magnetic flux. This is the cross-sectional area. Cross-sectional area. Now, I will just substitute the AB to the magnetic flux here. So we have here E, that's equal to 4.44, the frequency, the magnetic flux, which is area, okay, multiplied by the flux density. This is what we call the flux density in Tesla, okay, and then this is the number of turns. All multiplication process here. Okay, I will make use of this formula. This will be our working formula for this problem. Okay, so we have here primary, and this is primary. Remember, the unknown here is our N1. So our N1. What is our E1 in the problem? Our E1 is 250. So I will just put here 250. So we have here a constant of 4.44. 4.44. So we have here the frequency. How much is the frequency given? Let's see. Ilan ba yan? 50 hertz. That is the frequency. 50 hertz. Then what about now the area? The area we have, how much is that? 600. 600, this is 600. Remember, the 600 is in square centimeter. We are speaking of metric system here. In metric system, the area to be considered must be in square meter. It must be in square meter. So let us do some conversion here. In 1 meter, there are 100 centimeter. Then we have to square this also because this is square. Okay? Okay. So that is for the area. So that is for the area. Times the flux density. What is the flux density? 0.707. 0.707. Remember that the unit is in Tesla. Tesla. 0.707 Tesla. Then we have here our n sub 1. Okay. Well, you will see here that the only unknown is n sub 1. This is very easy in our calculator. Just use the shift solve. No? Okay. So I will calculate this. How much is this? Remember, this is 1. 1 squared simply 1. But there is 100 here. What is 100 squared? That is 100 times 100. I think that's 10,000. That's 10,000. Okay, let us manipulate this. So we have 250 alpha calc 4.44 times 50 times 600. Okay. 600, then let us consider the 100 x squared, then multiplied by 0.707, then multiplied by the n1, or just simply make it the alpha close parenthesis to declare as x. No? So we have shift calc equals. So this will be our answer. Our answer here is this. N sub 1 will be equal to 26.547. 547 turns. That is approximately, let's take a look at the choices. What are the choices? Okay, the answer would be letter A. Nearest 26.547. That is nearest to letter A. Sir Junel, no? That is my answer to your question.
Yes po.
27. There you are. No?
Thank you po. Thank you.
Okay, Sir Junel, that is my answer to your problem. To your
Yes po.
Thank you. Thank you.
Thank you. Thank you.